In this video, we're going to learn the algorithm for linear search. So this is an algorithm for searching an element in an array. But before we dive into the actual algorithm, let us understand this process through the help of an example. So here we have 5 lockers. Now behind each of these lockers, there's a number. Let's say there's a paper on which a number is written, right? Now we have been asked to search for the number 9 in these lockers. All right. So how you would go about doing that? So that is the topic of discussion in this video. So let us first get a few terminologies clear first. So the number that we have been asked to search, or the item that we have been asked to search, is often termed as the key, right? So this is the item or the element that we have been asked to search in our array. Okay, but here we are searching this number in these lockers. Now because all of these lockers have the same color or are identical, this is the reason why I'm gonna number them, right? So let's say the first locker begins from the number 0, the next locker begins from the number 1, the next locker is 2, the next locker is 3, and the last locker is 4. So in total we have 5 lockers numbered from 0 through 4. So let's search for this number, right? So how should we go about doing that? So we could start our process from here, from this end, or we could start searching from this end. So we would open the locker one at a time and see what's behind it. And then when we find the number 9, we can conclude that the element exists and it was found in this locker, right? So conventionally, we start searching from the first locker. So from this side, all right? So let's see what's behind this locker. Okay, so behind this locker we have 7, and that is not equal to a key element. So we move on to our next locker. So behind this locker we have 6, and even that is not equal to 9, right? So move on to the next locker. In this locker we have -1, and that is not equal to a key element, right? Let's move on to the next locker. Well, this locker, behind this locker we have the number 9, which is equal to our key element. So we have found our item in locker number 3. So that is what our output's gonna be. Key, or for instance 9 was found in locker number 3. So this is how you would search for an item if you are asked to search through these lockers, right? This is how we would do it normally. So this algorithm is just a formalizing of that approach, and nothing more and nothing less. Let's move on to the next slide. So let's understand this through the help of an array, how we would implement this algorithm in an array. So this array consists of the same numbers that these lockers had behind them. So the first element was 7, the second was 6, the next was -1, then 9, and then 11. And the size of this array is 5, which has been conveniently stored in a variable called n. And the number that we need to search, or the item that we need to search, is the key, which is 9. All right. So initially, and in this variable pos, we are going to store the position at which our key element exists. All right. Now, if the key element is not found in our array, then we are going to have a pos of -1, and that is the initial value of this variable. All right. So I'm going to copy this slide. Just a second. I'm going to copy this slide. I'm going to need it later. Okay. So this is going to be the initial value for the variable that would be storing the position at which the element is going to be found, right? Now, why -1? You see, the index of the array begins at 0. We cannot have a negative index for an array. This is why -1 would indicate that an element has not been found. So this is the initial value for this variable. And for all other variables, we don't have any initial value as such. So we start searching from the first element, and this is portrayed by the value I as 0. Now, which element is present at ARR I? 7. Now, is 7 equal to our key element? No, right? Our key element is 9, and that is not equal to the ARRI, ith element, right? So this is false, and we wouldn't update our pos because we haven't found our element as of yet. Now we're going to increment the value of I and move on to the next element, 1. Now which element exists at this location? 6. Is 9 equals to 6? No, right? That's false. Therefore, we are now going to update our pos. Now we're going to increment the value of I and move on to the next element in the array, which is -1. Now 9 is not equal to -1. Therefore, we do not update the value of pos and we continue searching because we haven't found our element as of yet. So we increment the value of I again and move on to the next element in sequence. That's 9. And 9 is equal to the key element, right? Therefore, what we do is we store the position at which our key element was found, and that position is 3, or the value of I. So we store 3 and we stop searching, right? This is the first kind of linear search. So this is case 1, where only one occurrence is required. On one occurrence of the element is required. This will be clear when we are going to deal with case 2, right? So let us write down a few observations first. Or before writing down the observations, let's take a case where the element is not found, right? So let's say the key element here now is, let's say 13. Now this number does not exist in our array. Let us continue with the dry run in the same way as before and let's see what the outcome of the algorithm is. So in the very beginning, pos has a value of -1. I starts with 0. Let's change the color. And the element at the ith location is 7. Our key element is 13 and that is not equal to the ith element. Hence, we do not update the value of pos and we move on and increment the value of I again. And we move on to the next element in our array, and which is 6. Now 6 is not equal to our key value. Hence, we do not update the value of pos and we move on to the next element in our array. We update the value of I by 1. So we get -1. And -1 is not equal to 13, which is our key element. This is false. Therefore, we do not update the value of pos. We continue searching because the element has not yet been found. So we update the value of I, move on to the next element, that's 9. And 9 is not equal to 13, so it's false. The value of pos is still -1. And we move on to the next element because our element has not yet been found. We move on to 11, right? 13 is not equal to 11. False. And we do not update the value of our pos. Now you see we have traversed through the array. So moving or accessing each element of the array once is known as traversing the array, right? So after traversing the array, we have found out that our key element does not exist. Now, how do we know that our key element does not exist? Because pos here has a value of -1 that it began with. It never changed, right? And this is an invalid index, which indicates that the key was not found, right? So what are the observations that we have found? We have seen that the value of I would run from 0 to n-1, where n is the size of the array, as is indicated from the dry run, 0 through 4, right? Now, each time we would compare our key element with the current element of the array. So we are going to compare our key element with the current element or the ith element of the array, which will be indicated by ARRI. And sorry, I've missed out something. The name of the array is ARR. We make that here as well, right? So that is another observation. Moreover, number 3, if the value of pos is -1 after traversing the array, that means a key has not been found. Pos is -1 after traversing the array, key does not exist. The element does not exist in the array, right? So this is a very simple searching algorithm, linear search, which runs in big O n time, right? Let's see the algorithm as in the form of a pseudocode, which would help us later in writing the complete version of this code. All right. So in this algorithm, there are a few things that must be said before. So ARR is the array of elements, n is the size of that array ARR, and key is the element that needs to be searched, and pos stores the let's write it here. It stores the index where index in the array where key is found, and the initial value of it is -1. So we start our loop, which would run from 0 to n minus 1 that we have seen before from the observations. I runs from 0 to n minus 1. So that's this. And then for every element of the array, we compare that with our key. Now I've changed the condition here, but it means the same thing. But still, for the sake of clarity, I'm going to change them back. All right, so we're going to compare our current element, that's the ith element of the array, with the key. And if a match is found, it means the key exists in the array. Therefore, we store the index of that element in pos, and we break. Why? Because the element has been found, right? And the very end, we display pos. And if the value of pos is -1, even after traversing the entire array, that would indicate that the element has not been found, right? I hope you have understood the linear search algorithm, and this is the pseudocode which later we're going to turn into a complete code. And I request you to, even if some things of the video, some aspects of the video or the algorithm are not yet clear, watch this video a couple of times, let's say 2 times, right? And then it will be clear to you. It's very intuitive. The algorithm is very intuitive of the fact how we would normally search through the lockers for finding stuff, right? So in the next video, we're going to see a program implementation in Java of the linear search algorithm. Well, till then, bye. See you later.